So the next couple of identities that we're going to look at are called the Pythagorean identities. And they come directly from the Pythagorean theorem on a triangle. So it's a pretty nice quick proof. So I'll just go through it here. So we've got our theta, and then with respect to theta, I've labeled the opposite, adjacent, and hypotenuse. So the Pythagorean theorem gives us that the adjacent squared plus the opposite squared equals the hypotenuse squared. And so what we can do with this equation is just divide the whole thing by the hypotenuse squared. So term by term, I'll divide by the hypotenuse squared. And I'll get 1 on the right-hand side. And we can just repackage those squares as adjacent over hypotenuse squared, opposite over hypotenuse squared equals 1. So I haven't really done anything there. But the adjacent over the hypotenuse in that triangle, that's cos theta. So that's cos theta squared. And opposite over hypotenuse is sine theta squared equals 1. And so what we've actually got here is, this is the Pythagorean identity, which I'll just write over here on the left. Cos squared theta plus sine squared theta equals 1. And that is true for all theta. It doesn't matter what. So you can try some, plug them in. You should see that that is always true. For the second identity, what we're going to do is start with this one and work our way down from there to generate a second one that's also really useful. So I'm going to start with cos squared theta plus sine squared theta equals 1. I'm going to divide this whole expression now by cos squared theta. And so what I'll get is 1 plus sine squared theta over cos squared theta equals 1 over cos squared theta. And if I rewrite this, I will have 1 plus, that's sine theta over cos theta squared plus, plus equals 1 over cos theta squared. And then if you look back to the previous identities, sine over cos is just tan. And 1 over cos is just secant. So this is a different version of this Pythagorean identity. So it's going to get added to our list here. 1 plus tan squared theta equals secant squared theta. And there is one more. So if we decided to divide by sine squared instead of cos squared, we'll get something similar. That second version, the tan secant one, is far and away the more common one, but we could do the same thing with sine squared theta. And we would get cos squared theta over sine squared theta plus 1 equals 1 over sine squared theta. And so this cos over sine squared, this is just cotan. So that's cotan theta squared plus 1 equals, and then 1 over sine is cosecant. So this would be a second version, a much less common version, but still true. And something to note right here, I don't know if we've touched on this yet. We see the little squares there in cos squared, sine squared, etc. So we've talked about this before, that cos squared theta is actually the same thing as cos theta squared, but cos to the -1 theta is not the same thing as cos theta to the -1, or 1 over cos theta. So remember, this is in fact the inverse function, which is not the same thing as a reciprocal function. So just be mindful of that. Sometimes You just have to be very attentive to the different notations that are used. Using these identities, we can prove a whole bunch of new identities. So yeah, using these simple identities, we can prove a whole bunch more big, complicated identities like what I've gotten written here. So this first one shouldn't be too bad. We've got cos squared theta times 1 plus tan squared theta equals 1. As always, we are going to split this into a left side, right side. And then work with the two sides independently. So on the left side, I've got sort of a big, maybe messy looking expression. On the right side, I just have 1. Usually your goal is simplify, simplify, simplify. So the right side, I can't really do anything with. It's 1. It's as simple as it's going to get. The left side, I can do quite a bit with. Now, a lot of the time, what you want to do is start by rewriting everything in sine and cosine. You can do that, but hopefully instead what actually kind of jumps out at you is this 1 plus tan squared theta, which is going to actually let us use this identity here, the 1 plus tan squared equals secant squared identity. You could turn it into sine squared over cos squared, and then you just have to do maybe a little bit more algebra to get the result that we're looking at. But this one works. I can just plug it in right now the way it is. And so what I get on the left side is cos squared theta times secant squared theta. And secant squared is just 1 over cos squared theta if we use the identities from before. And then we get 1 because everything's going to cancel out there. And that's my right side. And so I'm done. So that one's finished. I'm going to need a little bit more space to do the next one here. So I might just try to move this over. So on the one on the right is a little bit more involved. Now, in both of these, everything is actually already written as sines and coses, so there's not a lot that I'm going to be able to do there. I do see that there's a lot of squares and powers that are even, so that kind of indicates to me that I'll probably want to use the Pythagorean identity. There's nothing totally immediately obvious at first, but what I can see on the left is that that's a difference of squares. It's technically a difference of I don't know, whatever, things to the power of 4, but those are squares. They're squares of cos squared and square of sine squared. So I can factor that. So if I factor, I will get cos squared x minus sine squared x times cos squared x plus sine squared x. And then what I can see here, actually, the cos squared x plus sine squared x is in fact actually the original version of the Pythagorean identity. So this is actually equal to 1. So that's nice, because then what that means, I just have cos squared x minus sine squared x. Now this doesn't totally look like the right-hand side there, but it is sort of similar. What I'm going to want to do to move this to the right-hand side now is note that there's only sines in the right side. There's no cosines. So what I'm going to need to do is rewrite cosine as a sine to make it look like that. And that, again, is going to come from that Pythagorean identity. If cos squared x plus sine squared x equals 1, then that means that cos squared x is 1 minus sine squared x. And so I can actually just replace the cos squared x with that expression. So I'll have 1 minus sine squared x and then minus sine squared x. And so what we get is 1 minus 2 sine squared x, and that's the right side. So we're done. So that proof had a little bit more going on with it, but it had actually 2 applications of this Pythagorean identity. So it's kind of nice like that. Right, and so now we're going to be able to solve a different family of these trig equations where what we've got here is a mix of sines and cosines. So we have this mix. I've got a sine squared and a cos squared. So what we've got to do is turn one into the other. I am just going to clarify here. I'm going to ask for theta between 0 degrees and 360 degrees. And yeah, so what we have to do is change one trig expression into the other. It's a little bit tricky. Like if we look at the equations on the left, we could take that cos squared plus sine squared equals 1 equation and solve for cos, but we'd have to undo that square, and so we'd have this pretty big, messy looking square root function. So I don't really want to do that. What's actually going to be a little bit easier is to solve for the sine squared theta in that equation, because then all I have to do is really move the cos over. So sine squared theta is 1 minus cos squared theta. And if I plug that in, then my equation's all cosines. So I get 3 times 1 minus cos squared theta plus 5 cos theta equals 1. And then I'll just clean this up. 3 minus 3 cos squared theta plus 5 cos theta equals 1. And then I'm going to just move everything over to the right so that my cos squared term is positive. So minus 5 cos theta and then minus 2. So I have chosen this thing to be factorable. So I should get, let's say 3 cos theta, and I think that's going to be, let's see, I need a 1 and a 2 here. So I think that's going to be a plus 1, and then cos theta minus 2. And yeah, that should give me the minus 5 in the middle. So I have cos theta is negative 1/3, and cos theta is 2, which should get rejected because it's outside of the range for cosine. So cos theta is negative 1/2. Yeah, we should be able to solve this one. If you want, you can use a calculator to first try to figure out theta. So I could do theta is cos to the negative 1 of negative 1/3. And just get something here, because I know that 1/3, it's not one of my special angles, so the picture is going to need a little bit of work. And so what I'm getting for that is 109.5 degrees. And I did ask for it in degrees because it's sort of an ugly angle. And so what I'm going to do is then draw my reference angle picture for cosine to be negative. If I do my whole cast thing, that tells me it should be on the left side. So I draw my 2 triangles on the left. And if this answer here is at 109.5 degrees, then that tells me that the reference angle is 180 minus that. So that'll be 70.5 degrees. And that tells me that the second solution should be 180 plus 70.5, which is what, 250.5 degrees. And then so we get the 2 solutions, 109.5 degrees and 250.5 degrees. Yeah, so we can now solve this equation that's got kind of a mixture of trig in it.